Hello and welcome to our presentation about visual lidar odometry mapping, or V-LOAM, using an incremental KD-Tree or an ikd-Tree. So V-LOAM is a method with two sequential processes. The first uses visual odometry running at a higher frequency, such as the image frame rate, in order to estimate motion. The second uses lidar odometry at a lower frequency to refine motion estimates and remove distortion in the point clouds caused by drift in visual odometry. Our focus here is on improving the lidar odometry module. Visual drift is modeled as linear, but real visual drift behaves superlinearly, or it grows faster than linear. We believe more frequent updates should provide better results. And also, we are looking to say that improving computational load is also a plus.
Yeah, so V-LOAM uses the KD-Tree from FLAN, which stands for Fast Library for Approximate Nearest Neighbors. It uses an approximate nearest neighbor search for faster queries at the slight cost of accuracy. And the fact that it's static means that FLAN needs to be cleared and rebuilt every LiDAR odometry cycle. The incremental KD-Tree, or IKD, is a dynamic KD-Tree. This allows for insertion and deletion of points and automatically rebalances, downsamples, and deletes. In algorithms such as FastLeo2, where the ikd-Tree is fully implemented, results have shown that the ikd-Tree can be 20 times faster than the static KD-Tree rebuild. Here are some comparisons between the static KD-Tree and the ikd-Tree. In order for a fair comparison, downsampling wasn't used. And if you look at the figures on the right, you can see that even though the ikd-Tree has a slightly slower nearest neighbor search, allowing for incremental updates decreases overall time significantly.
So our proposal then is to just replace the FLAN KD-Tree that's in V-LOAM right now with the ikd-Tree. This should lead to faster LiDAR odometry and mapping, which are the parts that implement the FLAN KD-Tree. We're hoping that the faster LiDAR will lead to better accuracy, since it'll be correcting for the visual drift more often. And to compare the new ikd-Tree with the vanilla V-LOAM implementation, we'll be looking at the computational speed and the accuracy.
We base our implementation on the V-LOAM repository as shown on the screen. So this is actually a student's implementation of V-LOAM. And for the ikd-Tree, we use the official GitHub repository for ikd-Tree. So there are two sub-modules that we have to modify. The first is LiDAR odometry. So for LiDAR odometry, we first identify where in the algorithm does it use the tree. And we found that first, for LiDAR odometry, it does KNN search for each edge point and planar point. After that, V-LOAM will rebuild the entire tree. We base our implementation on these two Git repositories shown on the screen. The first is a student implementation of V-LOAM, and the second is the official ikd-Tree repository. For this portion, for this submodule, the LiDAR odometry module, we first identify where this tree structure was used. And the first part is where it does KNN search for each edge point and each planar point. After doing that, V-LOAM will then rebuild the whole tree. We could not implement the incremental updates for this submodule, and we believe the reason is for each point at the end of the sweep, V-LOAM has to reproject all of those points. So therefore, because all of the points have to be modified, we cannot just simply incrementally add on the new ones. Instead, we have to rebuild the whole tree. So for this part, we used the rebuild function of the ikd-Tree. The next submodule is LiDAR mapping. So we followed a similar process. We figured out where the tree structure was used. For this module, it first rebuilds the KD-Tree. So this is where we can introduce our improvements. Instead of rebuilding the whole tree with the new points, we can insert the new points incrementally. The next bit is the KNN search. So here we just replace the original KD-Tree's KNN search with the ikd-Tree's KNN search. we were not able to fully utilize the incremental updates. So therefore, we ended up using the rebuild function of the ikd-Tree.
So as a result, we test our ikd V-LOAM algorithm in 4 sequence of KT dataset. Well, it works pretty decent in the smallest dataset to the largest one. As evaluation, the trajectory plot, error, and row pitch yaw figure are shown here. As numerical result, we are focusing on translational RMSE and rotational error, which are smaller than 1% in most of sequence. And as in the processing time, we can see that the mapping time is consistently better among all 4 sequences, which is around 50 milliseconds. Although the KNN search takes more time in ikd-Tree, especially we are searching more points in leader mapping part than the leader audiometry part. I think here the main reason is because the time to build ikd-Tree is way smaller than the KD-Tree, especially we have more points in the mapping part, thus resulting in the biggest the main improvement in the mapping processing time. As conclusion, although we did some improvement in the calculating speed, but we failed to achieve our original goal of the incremental ikd-Tree. Well, we believe parts that contribute to this outcomes are, so first we have the wrong focus implementing the ikd-Tree. We should focus more on redesigning the V-LOAM module. And also, there are unexpected inconsistencies of the student implementation of V-LOAM with original paper, so which makes us a little bit more difficult to understand the code. So for future direction, we definitely can redesign the leader mapping architecture, then perhaps using environment EKF in leader audiometry module as fast layout, which fully utilize the ikd-Tree in their paper and then enable the incremental updates. Thanks for your listening. If you have any question, you can ask them now.